Now this puts me in a difficult situation, not that we had great speakers, but also this is not so much about the cutting edge technology, it's more on the contrary. We try to establish technology that we have and to industrialize it. So these are the topics that I want to give an overview about. So first of all, the motivation, why do we do proton therapy? Introduce barium particle therapy, the company that I'm working for. And then eventually get into some specifics of the cyclotron that we produce. And eventually, when we produce it, at the end of the process, we're doing the factory and commissioning and the acceptance testing of the cyclotron and show what we do before we deliver cyclotrons to site. And one of the reasons why I'm here, I guess, is because we're going to deliver 2 cyclotrons next year to the UCLH in London and to the Christie in Manchester. And so there's some relevance to that. So why proton therapy? And this is a picture, I do not have the reference of this. This was supposedly taken somewhere in the mid-40s. And this was neutron therapy. By that time, they didn't have available particles with high enough energies to penetrate deep enough into matter, and neutrons were the only radiation that was the only radiation available that would do the job. So when we start about history, and I think it's very interesting to go into history, and when we talk about particle therapy, we should admire the people that were participating to that or contributing to that. We have to start with probably William Henry Bragg, who gave the name to the Bragg peak that I will come to in a little bit. He was not so much known for the Bragg peak, really. He was the only laureate who received the Nobel Prize in 1915 together with his son for the X-ray diffraction on crystals. And that's what he is most known for. And then in the line I put Niels Bohr. Niels Bohr was actually the first one who did a quantitative assessment of how ionizing radiation loses energy in matter. At that time, he was doing it when he was working for Ernest Rutherford, and I guess I should talk about Rutherford being here. By the time he was working in Manchester, and that was yet a non-relativistic approach. But nonetheless, the important parts are already there. Which one is the pointer? If we're looking at the stopping power of protons in water, and this equation by him was later replaced by a relativistic version by Hans Bethe, which was then known by the Bethe equation or Bethe block equation, no mention of Niels Bohr. But if we're looking at how we lose energy in matter and looking at the energy range that we're interested about in clinical operation, up to about 250 MeV, we almost have a linear dependency here in the double logarithmic plot. So that is, we're losing energy with the reciprocal of the energy. And that actually is the reason why we have the Bragg peak, as I will show later. And then, again, Rutherford, we got to mention him being here. And eventually in 1920, he contributed to giving it the name protons after he assumed that nuclei would consist of positively charged hydrogen nuclei, and to separate that or distinguish that wording from the neutral hydrogen, he gave a new word term, and that in 1920 was then being called protons. So only since then we can talk about protons. And then about 10 years later, Ernest Orlando Lawrence is famous for getting one of the first cyclotrons to work and eventually patented it. Interesting to know that he wasn't the first to think about a cyclotron. That had happened already 10 years before, but at that time it was figured to be too complicated to produce. So he had the guts to make it happen. And what we see here is just the vacuum chamber. Of course, the magnet is not shown. And now that they had cyclotrons and they could accelerate protons into other ions to significant energies penetrating into flash, actually things were already ongoing in terms of clinical applications of ionizing matter. But then World War II came, all these people had been dragged into the Manhattan Project, and only after the war people picked up again on this idea. And it was then Robert Wilson who put up the seminal paper on the radiological use of fast protons in 1964, and which is really the onset of proton therapy. So I talked about Bragg and the loss of energy in matter, and I said it goes with the reciprocal of the energy. That means the slower the particle gets, the more energy we lose, which sort of results in an avalanche effect to the end. So we're almost losing no energy as we start off and start penetrating into the flesh. And as we get slower, it builds up very quickly and then drops off. And after this, behind this Bragg peak, we do not have any dose, and that's one of the very big advantages, as we will see. So if I want to distribute dose across a certain depth, what people do is they overlay several Bragg peaks to get what they call a spread out Bragg peak. And so you would target that across the tumor, and voila, there you are. If you compare that with X-ray treatment, you will see that X-rays do not only deposit a lot of energy even before and after, well, even before the target volume, but also still after. So it's not just that we deposit much more energy with X-rays into the healthy tissue, but also we have a hard time limiting it to the target volume. And what people do is to reach better homogeneity, they overlay fields from different directions. On the left side, we see the picture as we've seen before, and you can simply count on, evaluate the area that is covered here, and you'll figure that with X-rays you have about 3 times the dose that you deposit in the healthy tissue than in the tumor, whereas with the protons it's about 130% of that rate. And that ratio sort of keeps hold even if you do it with 4 fields, only 2 showing here. Then we still have much more energy deposited with using X-rays. So not only the healthy tissue is spared, but you can also direct it much better. So this is an actual planning example. Presumably there's something to be irradiated in the colon here. And with X-ray, this is an optimized planning coming from 3 directions, 3 fields. And there's the spine, and that is actually to be spared. And it's hard to spare that doing the X-ray because they're not stopping at any point. But if you're coming in with 2 fields from the proton side, protons will stop at some point and will not apply any dose behind that. And thereby, that way, you can easily spare organs at risk. And that really makes proton therapy a very good candidate specifically for pediatric cases where patients hopefully have still a long time span to spend, where you want to make sure that you do not suffer from secondary cancer. So, barium particle therapy. So I also start with a little history here. We started off with a company that was called Interatom, that was later on acquired by Siemens. That had its main business in nuclear technology, but nuclear technology was never very popular in Germany, so this is a protest about that the atomic companies would walk over dead bodies. I'm not quite sure what British people would say for that. So eventually this company got dissolved by 1994, and there was a management buyout for certain areas of technology, and that certain areas was superconductivity and RF resonators. These core competencies then went to Axcel, and Axcel was mostly equipping research institutes with their products. And it was kind of natural step to combine these things into something that could be an accelerator. So they had the vision of entering the proton therapy market with development of their own accelerator. So they started in 2001 a collaboration with the NSCL in Michigan, but also with the Paul Scherrer Institute in Switzerland and the Kernphysisch-Fresnel Institute in Groningen to resolve what is today's our cyclotron, and I will show you more about that later. This cyclotron was first installed at the PSI, but also parallel in our first proton therapy center in Munich, which eventually saw its first patient by 2009. But also this project was maybe a bit too large scale for a small company like Axcel, so they got into financial troubles, and that's when Varian stepped in. Varian at that point and still is the leader in oncology systems, so radiation with X-rays. And they want to make sure they have the prospect for the future, and they thought maybe proton therapy is it. So they acquired Axcel with the prospect of creating ProBeam, the product that we sell today as our proton therapy product. We are located in Troisdorf, Germany. That is a little south of Cologne, right there. We have about 200 people working in Troisdorf itself. That is engineering and manufacturing. And we have about another 100 people now working in the US. And these are really numbers I just guess, and they're changing on a daily basis. And maybe 30 to 40 people that are working internationally in service and installation. That is our current project charter. So we started off with the RPTC, and we installed our first ProBeam product in Scripps in San Diego. University of Maryland and Cincinnati just went clinical this year. And we have several under construction right now and many upcoming projects, and 2 of them really regard the proton therapy sites in London and in Manchester. So what is special about the cyclotrons that we're going to deliver to these 2 sites in the UK? And the honest answer is there should nothing be special about it, because we try to make it a serious product. But of course, just like with a car, it is a serious product, but it's not like you put in your ingredients at the beginning of the production floor and at the end of the conveyor belt that drops off a working cyclotron. It always needs individual treatment. And I will go into that. And what is the individual treatment? And that for physicists, it's a great opportunity to put in some physics here. So one of our categories that our cyclotron falls in, it's an isochronous cyclotron. That means the revolution frequency of the particles is always constant, no matter where you're looking at, as a function of radius. And obviously the trouble is, as you go relativistic and the inertia of the protons increases, you also have to increase the magnetic field to keep the frequency constant. Well, keeping the frequency constant gives you a lot of advantages. One thing is you can build a resonator that is explicitly made for this frequency, giving a high Q value that will allow us, in our case, to have an energy gain of 400 kilo electron volts per turn. And that also brings with it a CW beam, opposed to what you receive from a single cyclotron, where you have a sweeping frequency, then you only get pulses of beam. Okay, so that's the nice thing about an isochronous cyclotron. But now, how do we increase this B field with the radius? Well, the conventional approach always has been putting more iron as you go outside to the center of the plane. But that obviously limits your vertical aperture, and that means you're getting less protons out, and so that limits your extraction efficiency. But also what you can do is, now that we want to go to high fields anyway, because we want to have a compact machine, we make advantage of using a superconductive main coil, because as the iron saturates and is giving mostly a constant contribution to the magnetic field, we supersede or impose the air coil field of the superconducting coil itself, which increases as we approach the coil. And this is how superconductivity helps us to get this kink up here in the magnetic field. Now this looks very fine, but actually is a big problem. The problem is that the vertical focusing goes with the negative of the B field gradient. And as the B field increases, actually that means we have vertical defocusing. We wouldn't even get 5 turns before the beam blew up. So if that is the tune, obviously if this one is negative here, you get a problem with the square root of it, and that is exponential growth. What we do about it? The answer is the azimuthally varying field. So we introduce hills and valleys into the pole caps that sort of create a photostructure, because at every edge we see that we have a focusing and a defocusing part with a drift in between. Whenever we enter or leave one of these hills, we receive vertical focusing. And what it does to this formula we've just seen is it adds 2 terms really. The one term is just based on this photo experience here by entering and leaving it. But by giving it additionally a spiral shape, that is, we give it really edge focusing. We're adding a quadrupole component at the entrance and the exit of each of these hills. And this is this term up here. So by these means, we can add a lot of vertical focusing. And that's, of course, the clue how to stabilize the machine. Now, we have to consider 2 things eventually. we have to make sure that the machine is isochronous, and we have to adjust for the tune as we go outward. And how do we do that? So once the iron has been casted, and we're adding shim plates to it, and I will show you a little bit, and then we do the magnetic field mapping. So we have a tray here that rotates around it, a sled that goes forward and backwards, and it's taking about 230,000 measurement points, and that's the kind of field map that we receive. Well, first step is we're looking at the local deviations of the magnetic field compared with the average that is taken across all 4 sectors. And what kind of first thing that you see is that we have more magnetic field here than on the other side, and that is reflected in the first harmonic content as you go with the radius outwards. So outside we have a high field here, and that already is an indication that we need to move the coil inside the cyclotron towards the center, and after we centered the coil, we see that this first harmonic content is gone. But yet that doesn't have anything to do yet with what I introduced you to. So taking this map, we can do the simulations on how the proton evolves from inside to outside across the radius. And we're looking at the isochronicity, that is at the phase advance per turn. And this phase advance should ideally be around 0, but we see that it starts off at minus 20 degrees and somewhere around here reaches minus 5 degrees. A couple of turns here and we're out of acceptance and we're gone. But that's not even the worst thing. What we see here is that vertical focusing doesn't really work across the machine. We're looking at the vertical tune. It goes down to 0 here. Already here we have a blow off and the beam would be gone. So that cyclotron would obviously not work. So let's have a look how we fix that. And that's the individual treatment we give every cyclotron. So I mentioned we have this iron shim plates on each hill. And we apply 35 machining strips to each of these shim plates based on the calculation that I've just shown you. So from that calculation, someone tells, okay, we have to take away so and so much iron from each shim plate, and that is being done and remeasured again, and that's where we end up with. This is a different scale. This goes up from minus 20 to 10, and this is plus minus 1 degree. So we see that we are now pretty good around 0, and the phase advance of the beam is very confined. And also the vertical tune, these instabilities here have gone, and we now see that we have a nice vertical focusing, mostly constant throughout the acceleration, just before extraction around here. Kind of instability is wanted at the extraction because we need that for resonant extraction. So what are the characteristics of the resulting cyclotron? So we have a magnet that is wound of niob titanium, 40 kilometers of wire wound up into 2 coils around the medium plane, creating a central magnetic field of 2.4 Tesla, 3.8 Tesla at the hills. That swims in a bath of 100 liters of liquid helium. It's a zero boil-off system by 3 cold machines that we will liquefy every evaporating helium gas. We have an RF system. Already heard our talk about RF stuff. We now are using solid-state amplification, 72 megahertz. Nominal operating power is at 115 kilowatts by adding some more modules here that gives us a spare in case some modules would fail. And it's already included into 4 racks, while this is just a DC-DC converter we need for international installations. The beam, we extract beam with fixed 250 MeV. Beam current can be modulated for clinical use cases from 1 to 800 nanoamps. It could deliver more, but usually we don't want that. We have a high beam extraction efficiency, though honestly saying clinically typical values are around 60 to 70%, but we can reach 80%. I've shown that. And we can do some beam dynamic modulation. 3 meters in diameter, 1.6 meter high, 90 tons. So after we've done all that, we do some factory commissioning before the cyclotron leaves our factory and goes to site. Well, what is the history? We started with the coil winding. That is one of the very few things that we actually do on site because that is coming from our core competency. Then it is assembled. We go into the cold test and field mapping, things I've just shown to you. And then it goes into the test cell. This is an empty test cell, unfortunately. And in the test cell, we integrate the cyclotron with the hardware and the software control system, the same system that will also go with the cyclotron to the site. We hopefully establish beam extraction, and that is usually the time when you raise the glasses and give the cyclotron a name to it. And then we have beam internal acceptance testing. What is this internal acceptance testing comprising? Well, we have the factory test of main coil and verify that the cryostat is working as expected. I talked about the magnetic actions already, and then we get into the operation of the cyclotron. So show that everything works together. We do the conditioning of the RF cavity and also balancing out the D voltage. We have 4 Ds that do the acceleration in the cyclotron, and we have 8 units, 4 on top and 4 on bottom. So 1 degree of freedom is to match the frequency, and then you have the 4 tuners that you can use to create a sort of a first harmonic in the RF field to make sure that you get the same D voltage at every D for a homogeneous acceleration. And then we get into the beam commissioning. So we show that we can inject the beam, we can accelerate the beam, and eventually extract the beam. And we try to get to at least 30% of extraction efficiency in the factory before we deliver the cyclotron. And also what we want to establish is a broad working point, not just a working point, but a working plateau, where you can vary the properties or some parameters of the cyclotron without the beam getting lost and without the beam moving around so much. That is essential for the clinical operation eventually. And eventually also everything gets documented. So when the cyclotron is delivered to site, that you have a good set of starting parameters to the site commissioning. Well, and the last step is we prepare it for delivery. We have 2 of such boxes eventually that the cyclotron is being loaded into and delivered to site. Don't take me by these numbers explicitly because they could change, and it's not always clear to us which cyclotron is which. So as far as I know, the cyclotron that we call C14 is supposed to go to Manchester, to London. And that has just moved into the code test stand, and that's where we start with this process with field mapping and correcting for the magnetic field. Whereas number C13, I assume, is the one that will go to the Christie, and that has just moved into the test stand and will start beam operation soon. Well, targeted delivery dates are in about half a year from now for London and in a year from now for the Christie. Looking at the sites today, had a look at the webcam, actually had to figure out myself where these sites are. So for Manchester, it seems to be in the south of Manchester. Work is in progress. First room handover is scheduled for February 2018. Looking at London, it seems to be somewhere downtown London. Room handover here is for October 2018. Well, thank you very much for having me this talk here.
Very interesting, Mark. Any questions?
Hi. You talked about varying the energy initially, at least wanting to paint the tumour. How do you do that? Do you have a degrader or something?
Right. Let me see if I can go back to the overview. Well, probably we do not see much there. Yes, we have a degrader. We have a carbon degrader. That is the fixed energy beam is once it's extracted, one of the first things it sees is the degrader. That is carbon wedges we insert into the beam, and the further we insert it, the more material it has to go through before it leaves on the other side and has lost a certain amount of energy. As we recall the Bragg peak, the energy loss at the beginning is pretty constant. So that is the more, really, there's a proportional factor. The more carbon is in the beam, the more energy we lose. That's kind of a bad thing. It took so much effort to accelerate the beam, and then we put it through the degrader. We have a low emittance as we extract it, and after the degradation, we have a high emittance scattered beam. It's not very nice thing, but it's really cheap technology.
Really nice talk, thank you. So actually my question kind of leads on from that one, which is, are you in the future potentially trying to look at any technologies for dynamic variable energy extraction?
There are concepts around how one could do that. Some people go and use synchrotrons, but synchrotrons always have a spill and have not very high beam stability, and they always take room. Now, if you're looking at a site like London here, room is a problem. And actually for London, we have to make things much smaller than they have been before. So synchrotron is not a good option. Another option is to use FFAGs, but that's really just starting technology, and they need a pre-accelerator. And so maybe that is something that where things will go to. Another thing is maybe use a LINAC and add and activate several sections, so to stepwise accelerate beam. But that also so far still takes a lot of room, but is certainly an interesting idea. So far it's not yet commercially interesting, but maybe 5 to 10 years from now we'll talk about that idea very explicitly.
But in the cyclotron concept at the moment, you're not actively working on anything to do that in a cyclotron at the moment?
No. We're thinking about reshimming a cyclotron for different energies, but that's not something you could easily change.
Not with like a separate system of harmonic coils or something which would give you that extraction instability at a different energy? That's really kind of difficult thing to do. Yeah. Sorry to ask, one more question is, when you do your mid-plane measurement of the field, is that just on the mid-plane, or do you do an off mid-plane measurement?
No, we only do it in plane.
Okay.
Yeah.
Thanks.
Okay. One more question here, I think.
So what's the price tag of these machines you've delivered? And what do customers get?
The price tag, well, there's the price and the cost. And actually, I am not so sure about both of them because I'm not in marketing. I try to work on these things and make them work. Don't take me by the word. I think it's about 3.5 million for the cyclotron. And it's dissolved somehow into an overall price for a complete proton facility system. We usually do not sell the cyclotron as a standalone product. Sorry. And the second question?
Yeah, I was asking what's included in the price, but you just mentioned that.
Okay.
So.
Okay, any other questions? I've got a quick question. The ion source, what do you use to make the particles with, the protons with?
It's an internal PIG cold cathode ion source. So we insert hydrogen gas. We have a little small plasma burning that makes electrons panel around through a small pipe that we call chimney through the center of the cyclotron, and there's a little opening. And the hydrogen gas that is in there will be ionized by these paneling electrons. And hopefully with the pull voltage just at the surface of the opening in that chimney, we're pulling out the hydrogen atoms.
What sort of lifetime has it got? What sort of lifetime does it have?
The lifetime is about 2 weeks.
2 weeks. So
but the limiting factor seems to... Well, we're having some issues with the cathodes for one thing, that they're deteriorating with the time. But also what we see is that the chimney opening is burning out a little bit. So it's opening to one side, which means that the protons are getting out also at different phases, which are not desirable. So they will broaden up the beam, make bad contrast, bad extraction efficiency. So from time to time, we have to replace the chimney as well. Mm-hmm.
Okay, thank you. Any final questions? John.
Once this is installed in a hospital, how many people does it take to operate it? Just the accelerator bit.
So assuming everything has been installed and is working in a clinical way, just operating it really only requires an operator in the morning usually to bring it up from the overnight standby, if there was such a thing, like overnight standby, and go over the procedures and maybe half an hour work on it. And then the idea is that during the day, no more operator is needed. Fact is, we still need an operator from time to time for different reasons. One of the reasons is something trips, and we're not quite there yet with the automation that it recovers automatically, but still sometimes requires an operator to check out what has tripped. Is there something that he needs to do, or simply reset the error and make a note in the logbook that something was wrong and maybe have an eye on it. And the other thing is that it sometimes may occur that the calibration that was done in the morning is not good anymore in the afternoon, so sometimes it has to recalibrate it in between. Ideally, it would only be done once, and it's good for the full day at least. And then, of course, you have service. And that really depends on how well you organize the service people. You should always have 2 people around, and you have, I guess that would be sufficient to have 2 people for service around. You don't need them day by day. You have lots of other things that need maintenance. And if you need expert knowledge for the cryo system or whatever, RF system, you usually get those people in only by demand.
Okay, any other questions? Okay, let's thank Marc again.